Welcome everyone to the AMS Colloquium lecture series. My name is Ruth Charney. I'm president of the American Mathematical Society, and it is my honor to introduce this series of talks. The AMS Colloquium lectures were initiated in 1896, just 2 years after the founding of the American Mathematical Society. They consist of a series of 3 lectures given each year at the joint meetings that are designed to give a broad overview of important recent developments in the field. It is a great pleasure to introduce this year's Colloquium speaker, Professor Camillo De Lellis. Professor De Lellis is a permanent faculty member at the Institute for Advanced Study in Princeton, where he holds the IBM von Neumann Professorship. He received his PhD in 2002 from the Scuola Normale Superiore in Pisa, and after 2 years as a postdoc, he joined the faculty at the University of Zurich, where he currently holds an appointment as professor of mathematics in addition to his institute position. Professor De Lellis has made seminal contributions to the fields of geometric analysis and partial differential equations. His work has earned him an impressive list of honors and awards, including the AMS Bochet Memorial Prize in 2020, the International Feltrinelli Prize in 2021, the National Academy of Sciences Marian Mirzakhani Prize in 2022. In addition, he was an invited speaker at the 2010 International Congress of Mathematics and a plenary speaker at the 2022 International Congress. We are excited to have Professor De Lellis here today to give the first of his 3 colloquium talks. The talk is entitled Flows of Non-Smooth Vector Fields. Please welcome Professor Camillo De Lellis.
Thank you very much. It's a great pleasure and a great honor to be here for this series of 3 lectures, which I just realized has an impressive history from 1896. I mean, when I first heard it, I actually heard it like 1996, but I was thinking, that can't be possible. I mean, the AMS is certainly older than that. So, well, as the title of my lecture say, we're going to, I'm going to introduce you to a field which is concerned with defining flows of vector fields which are not necessarily smooth. So here is the problem which will be pivotal for all the 3 lectures. So you have a time-dependent vector field, U, on the Euclidean space, or we can think it's on the domain of it or on an n-dimensional manifold. Sometimes I will just assume it's on a periodic torus to avoid problems with spatial infinity, and I'm just looking at the associated ordinary differential equation, gamma dot of t, so the time derivative of the trajectory gamma is actually dictated by this vector field u at the position where the curve gamma is telling you you are. Okay, and as we learn pretty early, if you're following math courses at the university level, so there is a fundamental theorem which, depending on where you are, is called Cauchy-Lipschitz or Picard-Lindelof, which tells you that if this vector field u is Lipschitz regular in space, for which on the slide you see like the formal definition, then for every initial x, for every initial point where you are at the initial time in your trajectory, there is a unique solution of the ordinary differential equation. So, okay, so this is the solution not only exists and is unique, but it depends also continuously on both the initial data x and the vector field u. So you vary the initial data x, and the solution will vary with some continuity, and you change the vector field u a little bit, the trajectory will just change a little bit too. What is most important for us is that you can then define what is called the flow map, which is just bundling together the position of your trajectory at time t, assuming that you started at point x at time t equals 0. This gives you a map from time and space into space. If you freeze time, you just have a map from space into space, and it's a bi-Lipschitz homeomorphism of the space onto itself. So this means that the map phi is itself Lipschitz continuous, and it is bijective, and the inverse is Lipschitz. And actually, phi becomes more regular if you assume more regularity on the vector field u. So if you assume enough differentiability, you will have enough differentiability of the vector of the map phi. And of course, at time 0, the map phi is just the identity, because every particle or every trajectory starts at the point x. OK, so now here's the problem which is pivotal for this lecture and which is going to guide us also in the next 2 ones, is can we drop the Lipschitz regularity and still, like, get a good definition of what the flow of the less regular vector field is. Of course, there's another very famous result, which is a theorem of Peano, which actually tells you that if U is just a continuous vector field, there are always solutions. However, you also learn very quickly in courses that uniqueness fails very badly as soon as U is just a little bit below Lipschitz. So the typical one-dimensional textbook example is just the ODE gamma dot of t is equal to some root of the modulus of gamma. In such examples, as we will see, the non-uniqueness is fatal. There is no selection principle which actually gives you a coherent flow of trajectories. OK, so here's the textbook example that you find. So the time derivative of your one-dimensional trajectory is given by 2 times the square root of the absolute value. And you can just write down explicitly the solution. So if you start at x equals 0, you can choose to have the trajectory for positive time identically equal to 0, and then you can start off like a quadratic polynomial. If your initial datum is actually positive, then there is a unique solution for all positive time. I mean, you have to be that solution which I wrote over there. And if you're negative, there is a unique solution for small time, and the small time is detected by the time that it takes you to actually reach the problematic point x equals 0. And at that point, somehow, again, you have non-uniqueness. So if you plot in time and space a flow of your trajectories, so you see that if you're starting for positive x, the flow is kind of nice. So the positive half axis is mapped smoothly onto an half line which starts a little bit later than the origin. But then you see that there is a whole space, which in this picture is where I've declared there are the trajectories which start at 0, which is actually all filled with solutions of the ODE which was started at the origin. In particular, you can see that there is no way of defining a coherent flow which would give you a map like before, which is going to be nicely invertible with a nice inverse. For instance, the point 0 is mapped onto an interval at positive times. Of course, you could say, I can try to define a generalized notion of flow, and as long as you are on a one-dimensional situation, you actually can do a lot of things. But as we will see, what actually concerns us is the higher dimensional situation. Now, we'll argue that this example over here is in many situations a little bit misleading, because you will have an assumption which actually can rule out the fattening of this point 0 into an entire interval. OK. So here are some typical examples that are of interest for us. So you're looking at the evolution of a fluid, for instance, a gas or water, and under some assumptions, you know that the fluid is going to develop some singularity. So shock waves, detonations, cavitations, whatever. So now, the velocity field of the particles, this means it's not going to be regular anymore, but you still want to make a sense of what is the particle trajectories. Now, the bad news is that in these situations, actually the singularity that you're developing in these equations are even much worse than what we saw in the textbook example. So the vector fields that you're dealing with are often just discontinuous. And as we saw in the textbook example, not even continuity actually gives you uniqueness of the trajectory. But then on the other hand, there are some good news. So one good news is that we want actually to track the trajectories of most particles. We don't really often need to specify or to study the trajectory of every single particle. So you can think about this as I can give away a small set of initial points and actually care about most of the initial starting points. There are even better news. There is some guiding principle on the way you actually want to define your flows. So typically, these singular fields for which you want to define the trajectories have some approximation built in, which are coming from like approximation with smooth fields. Of course, as long as the vector field is smooth, we know very well what we want as a solution of the ODE because we have the Cauchy-Lipschitz theorem, which tells us that there is only one. And so what we're really interested in the end is to understand the asymptotic behavior of the flows for the smooth approximations, as the smooth approximation like reaches the singular one. Okay, so let me also mention another thing which is very classical. So if I look at this flow, which is the flow of a smooth vector field U, I can define what is called the Jacobian determinant. So I take the space derivative of my flow phi, and I compute the determinant of that. Okay, so a classical theorem by Liouville tells you, and for this theorem you can just assume that the vector field U is continuously differentiable, that this Jacobian determinant satisfies also an ODE. So the time derivative of this Jacobian determinant is equal to the divergence of the vector field U computed along the flow times the Jacobian determinant itself. Now, this actually tells you immediately that since you are in a smooth situation, the Jacobian determinant stays bounded and bounded away from 0. So in the smooth situation, assuming you have a uniform control on the modulus of the divergence of U, you can apply Grunwald's lemma. And recall that at time 0, the Jacobian determinant has to be equal to 1 because you're just looking at the Jacobian determinant of the identity map. And so your Jacobian is sandwiched between e to the minus ct and e to the ct. So of course, you can actually go further and further away towards infinity and closer to 0 as time t goes to infinity, but at least at every finite time, you will be bounded away from both. And another very interesting corollary is what is also called often Liouville theorem, which tells you that if your vector field U is divergence free, so if the divergence of U is equal to 0, then the Jacobian determinant is identically equal to 1. And by the change of variables rule in integrations, this actually tells you that the map phi is measure preserving. So it's mapping any set into another set with the same measure. Okay, so now for the purpose of this talk, I want to introduce a gadget which comes from measure theory, which allows for a very elegant formulation of Liouville's theorem and of its corollary. So I want to define what is the push forward of a measure. So the push forward, so assume I'm giving you a measure mu, and you can assume it's a very nice measure on the Euclidean space over which I have this flow of the smooth vector field, and I want to find the push forward. Classically, the push forward is defined. Oops, I've gone, okay, yes. So classically, the push forward is defined in the following way. If you're integrating a test function f against this push forwarded measure, what you do is you compute f on the point which is given by the flow, and then you integrate with respect to the measure mu. So a way of formulating the Liouville theorem is just to say the following. So say that I push forward the Lebesgue measure. Now, everything is nice and smooth. In particular, U is Lipschitz. So this push forwarded measure has a density rho. And the computation that we saw before of Liouville actually gives you a very nice partial differential equation for your function rho. So the time derivative of rho plus the divergence of rho times the vector field U is equal to 0. This is called continuity equation. And as people in PDE or like in mathematical physics it not only comes with an equation, you also have a quite appropriate boundary condition which transforms rho into a solution of what is called the Cauchy problem. So at the initial time, you'll have to remember that the flow phi was the identity map. So rho is actually equal to 1 because if I push forward with the identity map, the Lebesgue measure, I just have the Lebesgue measure. And so you have the initial data, rho at time 0 is actually identically equal to 1. Okay, so if divergence of U is equal to 0, you can actually rewrite the divergence of U times rho as the scalar product between U and the gradient of rho plus rho divergence of U, so that computation would always be valid, but if the divergence of U is equal to 0, that drops, and then you have U times gradient rho. And so the continuity equation transforms into another equation, which is called transport equation. And the reason why it's called transport equation is because if you have a scalar rho, which is actually solving that equation, that is equivalent to say that rho is constant along the trajectories of the flow. So in other words, you can make the following elementary computation. You take the time derivative of rho along the flow. And so first, the time derivative hits the time slot of rho, and then you have to use the chain rule to compute the derivation when it hits actually the space variable, and you find this formula. But now you have to remember that the time derivative of the flow is actually the vector field u along the flow. And now you see that I can bundle this together as the transport operator, so the time derivative of rho plus u scalar product with gradient rho, computed along the flow. And if I know that that one is equal to 0, then of course, here's the result. But I can also go the other way around. If I know that the function rho is constant along the trajectories of the flow, the left-hand side is equal to 0, and therefore the transport operator computed composed with the flow is equal to 0. But the flow is bijective, so that means actually that you're a solution of the partial differential equation. OK, so now note the assumption that the divergence of u is bounded is actually equivalent to u being Lipschitz in one space dimension. So all the textbooks examples that we saw are actually ruled out just by saying that we want to restrict our attention to vector fields u, which are maybe not smooth, but for which the divergence of u is under control. And there's a lot of reasons for doing that. So divergence of u bounded and the divergence of u equal to 0 actually covers a lot of interesting situations in which you have vector fields which are singular. For instance, if you're solving equations from incompressible fluid dynamics, you know automatically that the divergence of u is equal to 0, even though you might actually develop singularities. OK, so what is the first relaxation of the Lipschitz condition? So you can actually assume that your derivative of u exists, but it's not bounded. It's just slightly less than bounded. So it's LP summable, or it's even a radon measure, which we will call functions of bounded variation. So for me and for us in the rest of these talks, when I write down BV, I mean a function of bounded variation, which means I have a vector field u, which belongs to L1 and whose derivative is a radon measure. Okay? So the typical example of a function of bounded variation is a function that has a jump in one dimension. In higher dimension, the typical example is a function which has a jump on an hypersurface. Okay. So now to avoid technicalities about spatial infinity, let's assume that the domain is the periodic torus. Also, I don't want to assume that the domain is a boundary. So otherwise, I would have to actually state this theorem, which is due to a fundamental paper by Deperna and Lyons in 1988, and it was extended by Ambrosio in 2002 to the very relevant case of functions of bounded variation, that tells you that with this Sobolev regularity, and under the assumption that the divergence of u is bounded, there exists a very reasonable flow phi, which, however, is just measurable. And we will see, like later on along the lectures, that it's maybe a little bit better than measurable, but it's certainly very, very far away from being Lipschitz. On the other hand, this map phi is actually unique, and it's stable under approximation, which is what we wanted somehow initially. So we wanted to say, if I smooth out my vector field u, I have a very clear notion of what the flow should be, because there's only one by the Cauchy-Lipschitz theorem. And what this theorem is telling you is that this approximation will lead automatically to this generalized flow phi. Okay? OK, so what does it mean that the flow is reasonable? So here I'm actually using Ambrosio's axiomatization, which is a little bit different and more elegant than the initial one of Deperna and Lyons, although the groundbreaking ideas are all over there. OK, so what do I require on this flow? So first of all, I have to require that it's a solution of the ODE. OK, so I require that for almost every x, when I follow the trajectory gamma of t, which is equal to phi of tx, this is an absolutely continuous curve. Now, this curve has to start at the point x. That's my initial data. And of course, it has to solve the ODE. And now, if I have an absolutely continuous curve, I know that it's differentiable almost everywhere, and I can just write gamma dot of t is equal to ut gamma of t for almost every t. The assumption of absolute continuity is to rule out kind of silly examples in which, for instance, the function might have a jump It's differentiable almost everywhere. It might solve the ODE almost everywhere, but it's not a good notion of what is a solution of this ODE, because there's maybe a point in which I'm jumping from, say, x to a completely unrelated point, x tilde, which is not very meaningful. OK, so it seems like this is all that you would like to require. There's actually a third axiom in the theory. So you're going to require that this map that you have built, which is your flow, push forwards the Lebesgue measure with some bound which is not uniform in time, but on the other hand is bounded for every time. So if you remember this, OK, so first of all, in these lectures, we are going to call, like they are called in the literature, so these maps will be called regular Lagrangian flows. And now, you might notice that condition C, which we will call the Liouville axiom, imposes that these trajectories of the ODEs can be bundled together to form a reasonable flow. But in the classical theory, this is not something that you have to require, because you have Liouville's theorem, which is telling you that there is such a bound. Now, in the modern theory, this is actually a required condition. And we will spend some time on trying to understand whether this requirement is really needed or not. Okay. Now, there is a PDE-ODE relation, which is still very nice. So if you have a regular Lagrangian flow, a function rho solves the transport equation if and only if rho is constant along almost every curve T. I mean, almost every trajectory curve. And if you have a unique regular Lagrangian, so this is actually all under the assumption of uniqueness, I should have said. So if you have a unique regular Lagrangian flow, then you have a solution of the transport equation only if and only if you're constant along the trajectory. And if you have a solution of the continuity equation, then you're actually the push forward of some density times the Lebesgue measure through this flow. And you see the reason why I insisted on having a measure-theoretic version of this Jacobian determinant. Because phi is only measurable, but in my definition of push forward of the measure, there was no derivative of phi appearing. It was just a composition of phi with my test function f. And then I can define that for even for something which is not differentiable. And again, if you have a unique regular Lagrangian flow, then you solve the continuity equation if and only if. Now here, I was not so precise in the theorem. So if you have a regular Lagrangian flow, but is not unique, one direction is still correct. For instance, the push forward is going to fall to solve the continuity equation. OK. So now, it's very important that you notice something over here. So the density rho, which I'm assuming solves the transport equation, is in this space LP prime. So, and I'm assuming U in the Di-Pernat-Lyons theory is actually in W1P. So P prime is the dual Sobolev exponent. So you have this relation 1 over P plus 1 over P prime equal 1. OK, that's actually natural. But it's not completely optimal, we will see in a second, because by Sobolev embedding, you would actually allow for some exponents q less than p prime to still make sense of the equation. OK, so I will explore this more in detail, and I will give you precise definitions about this. Now, there's also a weaker form of the Liouville theorem, which still holds. So the classical Liouville theorem told you just because you're a solution of the ODE without requiring anything more, you actually can compute the Jacobian determinant of phi, and so, for instance, if the divergence of u is equal to 0, phi is measure preserving. But just under the assumptions that the divergence of u is bounded, you know that there's a compressibility bound for this flow. Now, the corollary over here is that, for instance, if divergence of u is equal to 0, I assumed as a given that my flow had a bound on the compressibility constants. I mean, that was like in the axiom C, what we call the Liouville axiom. But I didn't tell you that in the case of divergence of u equal to 0, phi would have to be measure preserving. This is actually a corollary of the theory, which is a non-trivial corollary. And the reason why it's a corollary of the theory is because, well, the density of the push forward of the Lebesgue measure would have to solve the continuity equation with initial data. And in this situation in which the Di-Perna-Lyons theory or the Ambrosius theory can be applied, there's actually a unique solution of the continuity equation. And well, rho identically 1 is trivially a solution, and so since the solution is unique, rho has to be equal to 1, okay? And that means, of course, that your map is measure preserving. Okay, so how do I understand the solution of these partial differential equations if I can't take derivatives, right? So, well, the solution of the continuity equation is understood in the sense of distributions. I'm not going to give you a formal definition for that. And the reason why I can understand that in the sense of distribution, you see, is because the derivative is taken outside. So I just need to make sense of the product of rho and u. That's why I assumed that there is enough summability for rho and enough summability for u so that the product of this is actually a summable function, so that it defines a distribution. And now you remember my comment that I was assuming rho is in L infinity LP prime and u is in L1 going into LP. Okay, then P prime and P match, but you remember that actually in the Di-Perna-Lyons theory, I'm assuming Sobolev regularity. If you assume Sobolev regularity, then the function u is actually more summable than being in LP. So I could actually lower the summability of rho and still make sense of the equation. So how do you make sense of the transport equation on the other hand? Well, you go back and unravel the computation that we did before. So the transport operator can be written as the divergence of rho times u minus rho times the divergence of u. Now, we know that the divergence of u is even bounded in our assumptions. So the product of rho with the divergence of u doesn't cause any problem. And the old piece, which was divergence of rho times u, doesn't cause a problem either. So I can understand that in the sense of distributions. Okay, so the theory also tells you actually more. So there's strong convergence. If you have Sobolev vector fields which are converging to a limiting Sobolev vector field, these regular Lagrangian flows, they are not only stable, but they converge strongly in the L1 sense. And that gives you actually a corollary, which is compactness. So if I assume uniform bound, I can extract a subsequence which is converging to a Sobolev vector field. And then I can use the theorem above to actually say that the regular Lagrangian flows are converging. So the space of regular Lagrangian flows under uniform bounds in these Sobolev norms is actually pre-compact in L1. Now, let me tell you a little bit how this Di-Perna-Lyons approach goes. So it goes in a sort of strange way because classically in textbooks, you actually first study the ODEs as characteristics of the PDEs, and then you actually use the ODEs, which you understand much better, to solve the PDEs. Now, funny enough, actually here we go the other way around. So we insist on understanding the PDEs and actually inferring from the PDEs something about the ODEs. So first of all, you actually understand, well, postness for bounded solutions of the transport and continuity equations, and then you derive from them the existence, uniqueness, and stability of regular Lagrangian flows. So now, there's something very easy, which is the existence. So the existence is a very soft regularization argument. So I can regularize my flow in a preferred way, in whichever way you prefer. I guess most people would just take the convolution of the function u with a smooth kernel. And I can regularize the initial data. And then I can solve the transport continuity equation in this case. I'm assuming divergence of u equal to 0 just for convenience, but it works even with two-sided bounds on the divergence. Okay, now the classical function rho epsilon is solving the PDEs in the usual sense is constant along characteristics. So the supremum norm of this function is certainly bounded. So if your initial data is between -1 and 1, your solution is always going to be between -1 and 1. So I can actually use Weak-Star compactness to extract some sequential limit for this guy, for subsequences. And now I use classical functional analysis to say that the limit is a solution in my sense. And that's because u epsilon is converging very nicely to u, and rho epsilon is converging in a sort of crappy way to rho, but the product is still OK. OK, now uniqueness is much harder. So here's the idea for uniqueness. So first of all, there is this property of solutions, which we are going to call renormalization property, which in the Di-Perna-Lyons theory for Sobolev vector fields is understood through some regularization scheme. So this is the hard analytic part, which needs a commutator estimate, which I will explain you in a few minutes. Now, why would I expect that if rho is a solution, the composition of rho with any function would be a solution? Well, if you go back, classically, being a solution means being constant along the trajectories. If rho is constant along the trajectories, rho squared is constant along the trajectory. So I can actually unravel my computation and discover that rho squared is also a solution. So it's something that you would expect. But of course, it's not something which you're going to be able to prove in the way you proved it, because I told you that I don't want to use the ODE. I will actually infer something about the ODE only at the very, very end, okay? Anyway, this is called renormalization property, and we will see if you have a non-smooth vector field, it's a rather non-trivial property. So if your vector field is very non-smooth, a weak solution or distributional solution of the transport equation will not have that property. We will discover that in the second lecture. Now, when you want to prove uniqueness, you use linearity to reduce it to the case equal to 0. If I have two solutions, I take the difference, and it's a solution for the initial time equals 0. But now, if you're, if rho, to show that rho is identically equal to 0, if the initial time is equal to 0, you observe that if you have this renormalization property, the modulus of rho is also a solution. Now you can integrate in space your equation. When you integrate in space your equation, because you have divergence of something that actually integrates by parts to 0. I mean, okay, I'm cheating a little bit. You have to assume something about the space. And then you discover that the time derivative of the integral of the modulus of rho is equal to 0. Well, of course, that, even if modulus of rho is a pretty crappy function, that tells you that the integral is constant in time. And since modulus of rho is positive, if rho is different from 0, this will tell you that rho has to vanish identically. Okay, so now how do I gain this renormalization property, which was the deus ex machina of my uniqueness? Well, so you know how to prove it by using calculus when you have actually smooth solution of the PDE. So one way you could try to do this is trying to regularize your PDE. So if I take a standard convolution kernel and convolve the PDE, of course, I still get the identity that you see over there, which is equal to 0. But it's not such a nice identity, because I first have to multiply u with the gradient of rho, and then I have to modify. Okay, that is not nice. It would be much nicer, so this is a trivial step, it would be much nicer if I had the equation that I wrote in red on the right-hand side. So now, instead of first taking the product and then making the convolution, I first make the convolutions of the two different pieces, and then I take the product. Of course, this is not what I had. But I can regard the equation which I like, I mean the left-hand side over there, to be true up to an error, which is the right-hand side. So the right-hand side, you see, it's a commutator, because I'm doing two operations in two different orders. First time, when I am on the right-hand side of the equation, first I'm taking convolutions and then product, and then I'm taking products and I'm convolving it. And I'm taking the difference between the two. Of course, the two operations don't commute. But you could hope that when I send the size of the convolution kernel to 0, right, so convolving with phi epsilon converges to the identity. And so hopefully the two things are actually converging to the same quantity, and the difference between them is equal to 0. Okay? Okay, so let me just give a name to this commutator. So I'm going to call it T epsilon. So now what would I like to do? Well, I would like to multiply both of the two sides, which I can do now everything is smooth, by beta prime of rho convolved with phi epsilon. So why would I do that? Well, I would do that because on the left-hand side, I can use calculus rules to actually infer that this is the time derivative of beta on my regularized function plus the advection with the regularized vector field of beta composed regularized function. So now, if I send epsilon to 0, the left-hand side is not creating any problem for me. It's just converging to what I wanted, which is the PDE for beta of rho. Now, what about the right-hand side? Well, the right-hand side, so here's where you have actually the hard estimates of the Perna-Lyons theory. It turns out that not the left-hand side, so that's actually a typo, but the right-hand side is converging to 0 as epsilon converges to 0, right? So this blue beta prime of rho star phi epsilon times T epsilon is actually converging to 0. That's what I want to show. That's not an easy calculation. It's not that difficult, so it's rather simple for Sobolev vector fields, even though it's a beautiful computation. And this is the original Perna-Lyons theory.
It's actually extremely hard for BV functions, and this was Ambrosio's main breakthrough in 2002. So it's a quite complicated estimate. Okay, now the Di-Bernal-Lyons approach also gives you stability. I want to go kind of quickly on this. So now you remember in the existence proof we had essentially weak star compactness of the solution, right? So that's how we actually got existence. So sequence of solutions which have a uniform bound are weakly converging to a solution. Now, uniqueness of the solution in the limit implies that you actually have weak star continuity of your trajectories, right? So because when I had compactness, I had to extract subsequences. But if I know that the solution of the limit is unique, now I don't have to extract subsequences because every subsequence will converge to the unique solution. So I have weak star continuity. Okay, so this means if I take UK, which converges to U, and I take a solution of the, say, transport equation, it will converge to the unique solution of the final transport equation. So here, what I'm swiping under the rug, I'm assuming that they all have the same initial data, or that the initial data converge in some nice way. Aha, but you remember that I have the renormalization property. So when I actually test my function rho k with any function beta, that's also a solution of the continuity equation. It's converging to some solution of the continuity equation. But the normalization property tells me that beta of rho is a solution of the continuity equation. And now the uniqueness tells me that is the unique solution. So now you see the phenomenon which is like very well known for people who are working on this type of problems. You have weak convergence of your functions, but you have weak convergence of every nonlinear test in this composition. So that together actually implies strong convergence. Okay, and then of course, once you have that, it actually implies compactness of solutions to the PDEs. So where's the ODE? Well, okay, at this point that you know all this stuff about the PDEs, you actually work out your relation with the ODEs through, like, you know, the push forward or through being constant along the trajectories. And you discover with a little bit of work that all of these properties, so compactness, strong convergence, and so on, actually get inherited by the flows too. So you want to prove that there is a regular Lagrangian flow. Well, then you regularize your vector field, you write down the usual smooth flows, and then the compactness will actually ensure you that you're converging to something. Well, that something is going to be the regular Lagrangian flow. And you want to figure out uniqueness. Well, you have uniqueness of the PDEs. You will actually have uniqueness of this flow too. OK, so now let me go back to classical. So there's a very interesting question by Bressani in 2002. OK, so you have this compactness, right? So, but how much is the space of flows compact over there? And that's actually a very interesting question because often compactness is implied by regularity. So for instance, the Sobolev space, W1P, embeds compactly in LP. So often having compactness means you have some form of, I don't know, higher regularity. For instance, like, you know, difference quotients of the function behave in a nice way. OK, in fact, Bressani in 2002 has a very nice conjecture with an explicit rate. OK, to try and understand how you can get hold of this problem, let me go back to the classical situation. So how do I prove uniqueness of the solution of the ODEs when I'm actually Lipschitz? OK, so let me say that I have two different trajectories, gamma and gamma bar, of a honest ODE. So assume U is C infinity. OK, so and assume the two trajectories start at the same point at time 0. You want to prove that they actually are always the same trajectory, so that gamma is equal to gamma bar. So what would you do? Well, when I want to prove that something is equal to 0, I differentiate, right? So I'm just a bloody analyst. I don't know what to do. But I know that the derivative of something is equal to 0 implies that this something is constant. And if it is equal to 0 at time 0, then it has to be equal to 0 always. So let me take the time derivative of the moduli of the difference. So that's actually very easy to bound as the moduli of the difference of the time derivatives. It's a very simple computation. And in turn, I know that that is equal to the vector field computing on the trajectory. Now, if I'm smooth, I know it's Lipschitz. So if it's Lipschitz, I can actually bound that one with a constant, times gamma of t minus gamma bar of t. And now, all of a sudden, I'm very happy because I just see an inequality between the time derivative of that function, the absolute value of the difference, and the function itself. And Gronwall's lemma is just going to tell me, well, wait a second, gamma minus gamma bar at time 0 was equal to 0. So now that has actually to be equal to 0. So that's easy. Now, can I do something like that when I am a Sobolev function or a function of bounded variation? Well, let me go back to this computation. This computation is still valid. And I mean, now let me even just assume something. I'm assuming, let me play the following game, which, in PDE is called a priori estimates. So U is infinity. So I could use the Lipschitz proof. But I'm kind of masochistic and I don't want to use it. So I'm just going to assume I can only use an LP bound on the derivative, but not a Lipschitz bound. So, well, if I have an LP bound on the derivative, there is this gadget, which comes from harmonic analysis, which is called maximal function of the derivative of U. So it's what I wrote there in this blue term. So what is this maximal function? So it's the Hardy-Littlewood maximal function. And the Hardy-Littlewood maximal function of a positive function simply does the following. You fix a point, and you take, for this positive function, the supremum of the average of that function f over all possible balls centered at that point x. And the radius is varying, OK? Now, there's something very nice and deep, which comes from Calderon and Zygmunt, which tells you that if p is bigger than 1, the maximal function, the LP norm of the maximal function, is bounded by the LP norm of the function. So you see, all of a sudden, I don't have a Lipschitz estimate, but I still do have some type of Lipschitz controls, because I have to evaluate this maximal function at some points along the trajectories. Well, of course, I might be unlucky. Maybe sometimes I'm evaluating this function on some point where it makes plus infinity. But then on the other hand, the maximal function is LP, so it shouldn't happen too often that I find these unlucky points. Well, I could be very unlucky, but in reality, it doesn't happen too often. So you can actually use, you can kind of dream of using some version of the classical Gronwall argument, which might work measured theoretically. OK. But it's pretty tricky. So none of the obvious naive things that you would try actually would work, which is, I think, also the reason why people didn't try this argument before. But in a work with Gianluca Crippa back in 2007, we actually found out that this heuristic can be made rigorous. And so you can actually study the Di-Perna-Lyons theory directly on the ODEs without passing to the PDEs. And it's actually interesting because this approach is not a subset and it's not a superset of the Di-Perna-Lyons theory. So there's some stuff which we can't do with this approach. For instance, you notice that p is bigger than 1. We can't recover Ambrosio's theorem. But there's some stuff which we can do with this approach, which you can't do with the Di-Perna-Lyons theory. For instance, you can prove some interesting theorems when, say, U is a singular integral kernel convolved with a measure. Now, Bressan's conjectured rate for the compactness of the flows is actually correct for W1P with p bigger than 1. When I solved this, I was so happy, so I just asked Alberto, because Alberto gives you, I think, $100 if you solve actually his conjecture, which is for p equal 1. So I asked Alberto why p equal 1, and just told me, I don't know, it looked more natural, but I wasn't expecting there's any difference. Anyway, he didn't give us a penny, even though we solved the p bigger than 1. So now, it actually has a very interesting, so this proof actually has a very interesting information which doesn't come from the Di-Perna-Lyons theory. I can quantify the compactness, but I can actually quantify some regularity for this flow phi, which it was only measurable. OK, so it actually is losing Lipschitz in a quantitative way. So you will see the combination of these two names, losing and Lipschitz. So what I'm telling you is the following. So p is a fixed number, which is bigger than 1. Then there is a constant c, which is going to depend only on this summability p and on the dimension. And what can I do with it? Well, it's an a priori estimate. I mean, of course, you can even transform it into an estimate for the flow, for the regular Lagrangian flow with the limit. But let's stick to the smooth situation. So assume U is a smooth vector field, and phi is the corresponding flow. Now I can play the following game. So for every epsilon bigger than 0, this is the losing part. So phi, say, if it were only measurable, from losing you would know that you can give away a set of small measure, and on the complement, your function phi would be continuous. Now I'm going to tell you the following. So you can give away a set of small measure, and on the complement, the flow is Lipschitz with a crappy constant. I mean, it's very bad. You see you have this constant, and then the exponential of what is under the bracket. There is a dependence on the LP norm of the derivative of u, but there is a dependence on epsilon, right? So you let epsilon go to 0, and this blows up like an exponential. But it's Lipschitz on the complement of that, which is almost gaining one derivative, right? So you see that, okay, so you see that, so if you do it in this way, you see that if p is equal to infinity, so if you're Lipschitz, epsilon to the 1 over p becomes epsilon to the 0. And constant times LP norm of the u becomes constant times L infinity norm of the u. And so you recover the Cauchy-Lipschitz theorem or the Picard-Lindelof theorem, naturally. Now, what does it mean that, right? I mean, it looks like, so if I had like a Sobolev function, I would be losing Lipschitz, but the constant, the Lipschitz constant, would go like a power of epsilon. Now I'm losing this exponential. So what the hell is happening? Well, you can actually prove, so this was proved by Brescian, Jabin, and Léger, that it looks like having a log of a derivative. So if you take the Fourier transform of your flow, being Lipschitz means, I don't know, being W12 means I take the Fourier transform of the flow, I multiply by the modulus of psi squared by the modulus of the frequency, and I get that I'm summable. So now I've actually gained the logarithm of a derivative. And this is all equivalent, and this is a paper by Brouet and Guyen in 2009. It's actually equivalent to Gagliardo semi-norms with a log. So the upshot is I've gained in derivative in the logarithmic scale, which looks like a very lame result. It's like, okay. So when I was in 2007, I just thought, this must be crazily suboptimal. It's just because we don't know how to do the estimates. But I mean, this flow ought to be better than S. But actually, these rates are all optimal. And that was very surprising to me. So this has been proved in the full range of exponents by Alberti, Kripa, and Mazzucato, and with a different proof and for a more limited range of exponent at the same time by Yao and Zlatosh. So it's very interesting. But the rates which are conjectured by Bressan, which are matched by this theorem, they are all optimal, actually. Well, optimal in terms of the rate, not the constant. The constant, God knows about that. Okay, so now let me go to the conjecture which would gain you like $100 from Alberto. So this is a way of actually stating this conjecture. So say that you take your function u on the periodic torus, and you can consider it's the periodic two-dimensional torus. It's a divergence-free, and it's a smooth vector field, because the nice things about this is that it's really an a priori estimate. So you can tell it to an undergraduate student after you teach the undergraduate student second year calculus. Anyway, I'm telling this to every PhD student and postdoc, so the number of people who actually know about this elementary problem keeps growing. Okay, now partition your torus into two reasonable regions, so A and B. Essentially, you're like cutting it into half. Okay, so now here I'm just introducing a concept which I think people in dynamical theory, they're always like bothering about, but I wasn't bothering about this until I bumped into Alberto's conjecture. So I'm just going to say that phi mixes at scale epsilon. If anytime that I put a small disk or a small ball of radius epsilon somewhere, and I look at the image of the set A through this flow, 1/4 of the disk is occupied by A, and no more than 3/4 of the image of the disk is occupied by A. Now, this flow phi is measure preserving because the divergence is equal to 0. So the image, the other half of the ball has to be occupied by B. Okay? So the idea is that every time that I locate a ball of radius epsilon, I see, even though epsilon is very small, a portion of A and a portion of B, non-trivial. So it's mixing A and B, it's steering A and B in a very efficient way. Okay, now the conjecture says there is a constant which depends only on n, which does the following. If u mixes at scale epsilon, the integral of the modulus of du from time 0 to 1 and over all space is bigger than c, this constant c times the log of epsilon. In particular, if you have a uniform bound on the L1 norm, you can't mix at an arbitrarily small scale, okay? But in a quantitative way. So now, our paper with Gianluca gives you an estimate of the same kind in which LP replaces L1, and unfortunately, the constant now is going to depend on P2, okay? And it becomes worse when P goes to 1. It becomes worse in the typical logarithmic fashion with which, like, say, harmonic analysis estimates like go wrong when P approaches 1. So essentially, if you look back to what we were doing, we were using Calderon-Zygmunt to estimate the LP norm of the maximal function with the LP norm of the function. And Calderon-Zygmunt goes wrong when P approaches 1, and this goes wrong in the same fashion. Okay, so now there's a stronger version of this conjecture, which instead of assuming that the divergence of u is equal to 0, which would have the effect that phi is measure preserving, just assume that the Jacobian determinant of phi has a lower bound and an upper bound, which is not really equivalent to say that the divergence of u has bounds from above and from below. Okay, so a corollary of this stronger form would be that the Di-Perna-Lyons-Ambrosio theory holds for nearly incompressible functions of bounded variation. So if you remember, we assumed that a bound on the divergence, but here I'm only assuming a bound on the Jacobian. So this would be a corollary of this conjecture, and this was a corollary that quite a few people worked on because it would have pretty nice consequences, and it was also a conjecture of Alberto. That is called Bressant's compactness conjecture. So you might wonder, how do I encode the fact that my vector field u is nearly incompressible? Well, you have to remember that the Jacobian determinant is a solution of the continuity equation. Since you have comparison principles between solution of the continuity equation, because the ratio between two solutions of the continuity equation is a solution of the transport equation, which satisfies the maximum principle, having a uniform bound on the Jacobian determinant is equivalent to say that there is some solution of the continuity equation which is bounded away from 0 and from infinity. So it's something that you can actually very nicely formulate in terms of PDE. And why were we interested in this? Well, because there's lots of PDEs in which this solution of the continuity equation is given to you for free. For instance, Alberto is a famous name in the theory of hyperbolic conservation laws, and in the theory of hyperbolic conservation laws, often densities like that are actually given to you from the data of the problem. So there was an intrinsic motivation for studying this problem. Okay, so we had partial results on this. So Luigi had partial results with me. We had work with Jan Mali, and Luigi had a wonderful work with Gianluca Crippa and Stefania Maniglia. And we all kind of covered some partial results. And this actually, this compactness conjecture was settled by a very deep result of Bianchini and Bonicato. So they proved the compactness conjecture, which, if you go back to Bressant's conjecture over here, one way of stating it is, I can't quite tell you that there is a log of epsilon for that bound, but I can tell you that the integral is going to infinity as epsilon goes to 0. I just can't quantify it, okay? And so Luigi's theorem is doing that under the assumption that divergence of u is equal to 0, and Stefano's and Bonicato's theorem is doing that under the assumption on the Jacobian. Okay, so that pretty much closes the lecture for today, but of course, with all good, if you're looking at some, so I'm pretty nice compared to modern TV shows, because typically they just leave you on a cliffhanger. So on something, I didn't leave you on a cliffhanger, but I want to give you a teaser for what is coming. So in the next lectures, we are going to explore the boundaries of the Di-Perna-Lyons theory. And you saw that there's a series of interesting questions which came out from my presentation. So one was, is it possible to improve the summability ranges of solutions of the continuity and transport equation compared to the vector field? Okay, so we had a uniqueness and stability result under some summability assumption. Can we drop them? Another very natural question is it possible to drop this Liouville's axiom for regular Lagrangian flows? And that is actually equivalent to the following, which is a popularization of the de Perna-Lyons theory. So often people say the de Perna-Lyons theory is equivalent to show that there is a unique trajectory of the ODE for almost every initial point. Not really. If I could get away without the Liouville axiom, that would be literally true. And it's in fact equivalent to that. Okay. Now, of course, the biggest question that a lot of people would be interested in is, can we actually lower the regularity even more? Because, okay, we have W1P, so it's not Lipschitz, but it's still having one full derivative, which is just LP integrable. It would be, in particular, interesting and very worthy for a lot of applications to just know that I can lower it to maybe some fraction of a derivative. So, for instance, like, Hölder functions. That would be wonderful. Well, even when the answer to the latter question is negative, so even when you have U, for which you don't have any de Perna-Lyons theory, you could actually ask the following question. So all we are interested in is in identifying what smooth approximations of my problem lead to. So can I actually hope that there is a selection mechanism for which, okay, maybe I have two solutions of the transport equation, but there's one which is always picked up by some good regularization, okay? Well, if time allows, in the last lecture, after we have explored all of these questions, I actually want to show you a cool application which is very recent of all of these questions, just to also motivate the fact that it's not only for theoretical purposes intrinsic to this. So an application of irregular mixing flows, so something or things which were actually invented for making counterexamples to the anomalous dissipation for the forced Navier-Stokes equation. Okay, so that was the teaser, and now thank you for your attention.
For an excellent first lecture, and looking forward to the next two. We have just a couple of minutes here if anybody has questions. There are microphones in the aisles. If anybody would like to ask a question, please come up to the microphone. People a moment here. No questions? I guess it must have been an extremely clear lecture. Nobody has any questions.
Thank you.
So in that case, let's thank Professor De Lellis again.
Thank you.
Great.